Testing, testing, 1, 2, 3, 4. Testing, testing, 1, 2, 3, 4. Okay, welcome to today's machine learning class. Before we start, I have some announcements to make. Okay, first is about homework 3. I understand that many of you are working hard on homework 2 now, and we are planning on announcing homework 3 this week. Yay! Okay, maybe not EA. It would be somewhat in parallel with homework 2, but we need a few more days before we can announce homework 3. Having said that, you will have more than 2 weeks, okay, to complete your homework 3. So homework 3 would be due 2 weeks after homework 2's deadline. Okay, so there are some overlapping. I'm hoping that's fine because I understand many of you would have midterms this week or next week and so on. So we're hoping that the overlapping would help you manage your time better during this midterm season. So that's one thing, but we will probably not announce homework 3 today. Okay, we need 1 day or 2 more before we can finalize it. That's about homework 3. Then, because of the delay in terms of the deadline of homework 3, we will announce homework 4 later. So homework 3 would be announced after homework 4 will be announced after homework 3 is due. And we go back to the 2-week per homework pace. That being said, we will need to cancel homework 7. Okay, so we will only have 6 homeworks. Yay! Okay, so hopefully you understand that this is our adjustment both with respect to the pace that we are taking in teaching and also to balance all your needs like midterms and so on. Actually, to balance ours too, okay, mine and the TA's loads as well. That's the homework part, so we will have 6 homeworks, and we are planning for the final project that's going to be announced soon. Starting this week, actually after the class, I'll send another announcement telling you how to register your team. Basically, we will have we will want you to form 3 people teams. Okay, if you want 2 or 1 person per team, that's fine. Okay, but we will evaluate your final project report based on the workloads or based on the expected workload of a 3 people team. So if you are a 1-person team, then you may need to do triple of the works to complete your final project reports. That's the usual design of our final projects. And for those who find it hard to identify team members and so on, we will initiate a thread in NTU Cool to help you find the matching team member for your team. But basically, all the team member matching should be done by yourself under your mutual consent and so on. Okay, the TAs and I will not force anyone to be with any team. Okay, we basically believe that we have the flexibility. We want you to form a 3-people team, but we can allow 2, we can allow 1. We have the flexibility, and it is your responsibility to find a matching team member that you would find comfortable working with. Okay, so that's the policy that we are going to take with respect to the final project setting. Okay, so that's about all the housekeeping items I want to mention about homework and also about the final project. And I understand some of you want more convenient TA hours, especially in terms of English-speaking ones. And we actually gave some deep thoughts about that. And having gathered the information from the TAs and also from some students about the current situation, we decide that our current TAR setting is flexible enough for the whole class of students. Okay, we have enough English prioritized TA hours to help proportionally to the international students that we have. We have started some physical TA hours to help those who want to meet the TAs face-to-face. And we have virtual TA hours online as you have experienced as well. Okay, so we have some diversity there. And although we really want to satisfy everyone's need, we need to understand that TAs are limited and privileged resources, and we simply cannot ask the TAs to satisfy everyone. Okay, so we will keep the current structure unchanged, but please bear in mind that all our TAs in their TA hour setting are language friendly. Okay, we have some TAs, although their TA hours may not be English prioritized, they are English friendly as well. Of course, it's super hard, okay, to communicate in English because for most of our TAs, their mother tongue is not English, and therefore, if you are international students, the TAs could have some barrier in understanding your questions and making their answers understandable to you. But I trust that all our TAs are doing their best in terms of this communication, and I understand there must be frictions, okay, in terms of like how the communication is done in terms of those language barrier, but we have asked our TA to be language friendly, okay, meaning despite of all the difficulties, okay, the TAs would do their best to understand, to provide useful answer to you to the best we can, and we ask for a little patience, okay, in terms of this communication. And if you find it hard to communicate with some of the TAs because of the language barrier, please go to the other TAs who might be more familiar with English, or please send an email to me and I'll try to respond to them basically in text form clearly for you. And hopefully my English communication skill is a little bit more experienced than our TAs to provide you with useful answers. So that's what we're going to do in terms of how to use TA hours to help our students, especially our international students. Okay, so that's the current situation, and I'm not sure if our microphone is a little bit okay. I see from my microphone bar that the sound will be a little low and so on. I adjusted it, and if there are any issues, let me know. Okay, and let's see. Okay, so let's get started with today's lecture. Last time we extended the linear models for binary classification and regression that we have learned to multi-class classification, and that's basically completes our linear model toolbox. Okay, you have linear models for binary classification, for multi-class, for regression, and you will actually find that with those tools, you can conquer lots of realistic problems that you may face if you can shape them as binary classification or multi-class or regression. Actually, that counts as maybe 80% of the initial problems that I have seen in the industry domain. And now we are going to do another important thing. Okay, we are going to extend linear models to nonlinear models. Okay, so basically we understand that linear models are useful, but they are limited. Okay, there are data sets where, okay, at least if I give you the right-hand side data set here, visually you will say that the linear model is doomed to not do well, okay, simply because it doesn't seem to be separable to by a linear boundary. And we may want a nonlinear boundary, something like this, okay, to separate our data, or at least to our human intelligence, it appears to be the right thing to do. So the next topic we're going to discuss is how we construct nonlinear boundaries. Now, before we start with nonlinear boundaries, let's introduce a new concept, okay, that extends the linear separability that we have learned. Basically, for this boundary, for this data set, we see that it is not linearly separable But okay, if we are willing to use a big circle, a big circular boundary to separate the circle from the cross, we should be able to do that and actually plotted the result on the right hand side. So I can use a circular boundary, and actually this is a very particular circular boundary that's centered at the origin. Okay, so there's the center at the origin, and I'm marking the length here, and you see that this is a circle with radius 0.6 centered at the origin to separate the little circle and the little cross. Okay, that's one of the separating boundary that we can look at for solving this problem. And if you list the equation of this particular circular boundary, the equation would look like this. So you see that this part, okay, marks that the boundary is circular, and within the big circle we have plus. That is, if the this is radius square, right? Okay. Sorry. Maybe I shouldn't describe it as radius square. This should be. Let me raise it a bit. Okay. This should be distance square, okay, where the distance is the distance to the origin or the distance to the center of the circle. So if the distance is smaller than 0.6, okay, and this is negative distance squared. So if the distance is smaller than 0.6, then the inner term would be positive, which means the sign would give us circle. And if the distance is larger than 0.6, okay, it means the point is outside of the circle, and the sign would give us a cross. Okay, so you can verify that this equation exactly gives us the intended separation that we want. Okay, basically inside the circle, blue. Okay, outside of the circle, red. And with this equation, of course, what we can do is to define some similar equations and form a hypothesis set. Okay, form a circular hypothesis set that contains all circular boundaries, and then rederive perceptron learning algorithm or logistic regression or whatever, okay, with respect to those circular hypotheses. But as you can imagine, after we have spent so many weeks deriving the linear models, it would be a little bit too much, okay, to just sit there and rederive perceptron learning algorithm in the circular mode, rederive regression in the circular mode, rederive logistic regression in the circular mode, and so on. So the next, what we're going to do is to introduce a systematic approach for extending all the linear models that we have learned to take circular or even something beyond circular boundaries. Okay, so we emphasize that it is a systematic approach. Okay, much like the 1 versus all or 1 versus 1 that we have learned last time, is a systematic approach, a meta algorithm that works on top of algorithms. By the way, you see that meta is a very, very famous term nowadays, okay, meaning something beyond. Okay, so of course, some company take it to mean it is going beyond what its current products are offering and doing something much bigger. And for here, we are taking something beyond the basic perceptron learning algorithm or linear regression or whatever we have learned, okay, to basically couple it within a bigger framework, okay, the meta framework basically, so we can systematically extend any linear model that we have seen to a nonlinear mode. Okay, that's what we're going to do next. How do we do that? What we see here is that the equation we used, okay, to write down the particular hypothesis that we're interested in can be decomposed to two parts. Okay, one part is the coefficient, the 0.6, the -1, the -1 here, and the other part is related to the features that we're interested in. Okay, so for example, you see x1 squared, you see x2 squared, you see 0.6 where you seem to not observe any x, but our little friend x0 can help here. Okay. So we have parts that are related to the features, although it's the relation is not a linear relation, and we have parts that are related to the coefficient, okay, in terms of combining those. What we're going to do here is to do some renaming. We're going to rename this x1 squared by z1. We're going to rename this x2 squared by z2. And we're going to rename this constant 1 here, which is x0, by z0. Okay, so if you can see here in the notation of z, what we're simply doing is this z vector, which contains z0, z1, and z2 with some coefficients. I'm going to deliberately name the coefficients as w, w0 coupling with z0, w1 coupling with z1, w2 coupling with z2. To distinguish those w from the w that we have used in the original linear models, I'm going to mark those w with little tilde here. Okay, so this little tilde marks that we are operating this w along with z. And then with this notation, we again see that we can write things down in a vector form. In particular, within the sign, what we're doing is to take a vector of z, do inner product with the vector tilde w, and we get the hypothesis. That's the that's the transformation that we're going to take here. Why is that? If we can express the hypothesis as an inner product form where one part of the inner product are coefficients that can be learned by some algorithm, that's the w tilde part. And the other part is the values that can be computed from data. Then essentially we are doing a linear model, but it's a linear model in the z space. I'm emphasizing that it's a space because for every x we can correlate it with some point z in another space. But what we're doing here is essentially, okay, so then let's change our mind. Okay, we cannot do linear classification in the x space because things are not linear separable, but we can do classification in the z space linearly because, okay, in the z space, this particular boundary can separate all the circles and cross that we have on hand perfectly. So this is the idea, okay? If the original x and y are circular separable, then the z space data will be linearly separable. For example, in terms of this particular x1, okay, if we convert it to the z space, then we get something like z1 here, okay, saying it's a circle and it falls somewhere. For this point x2, we can convert it to the particular z2 here. For every example that we have on hand, we can just convert it to z, and then in the z space, there is just a single line where the equation of the line is 0.6 plus, minus z1 minus z2, and taking the sign. Okay, that's the hypothesis that would separate the circle and the cross easily in that new space. And this is called a nonlinear feature transform, and we are going to give it a particular symbol that we call phi. Okay, And this phi transforms every point in the original X space to a Z space. Of course, we're talking about a very particular transform here where we just take the zeroth component being 1, the first component being the original value squared, and the second component being the original second component squared. Okay, so it's a transform. A transform is just a function that converts our original examples to another space. A circular separable X, so being circular separable in X would then mean being linearly separable in Z under this particular transform. Now you may want to ask, okay, how about vice versa? If I can find a line in the Z space, in the particular Z space that we just constructed to separate our examples, would I get, or would I always get, a circular boundary in our original space? Well, think about this. Okay, we have listed the function for making the transform. Okay, the particular function we're considering is 1x1 squared, x2 squared, and so on. That is, the hypothesis set that we're considering is essentially w0 plus w1 x1 squared, that's z1, and w2 x2 squared, that's z2. Okay. And technically, I should pronounce tilde w0, tilde w1, tilde w2. But as you can see, pronouncing with tilde everywhere just sound a little bit overwhelming. Okay, so generally, I would pronounce w, okay, unless we really need to distinguish tilde w and w. Okay, now with the variation of all different kinds of w here, originally in the linear space, we are forming different kinds of lines, right? You can have lines that are of a positive slope, lines are of negative slope, and so on, all kinds of lines. Now, by varying w0, w1, w2, in those hypotheses, we can actually get different boundaries in the original space. For example, the boundary that we have obtained is based on 0.6 as w0, minus 1 as w1, minus 1 as w2. And that's a circular boundary with little circle being inside. How about if I just negate all the coefficients? If I negate the coefficients, the boundary would look the same. But now the little circles are outside. The blue regions are outside. The red regions are inside. So this is much like when we negate the coefficients of a particular line, then the the blue region and the red region would change their roles. But we have also other possibilities. For example, okay, if I take w1 to be different from w2, then from the equation represented by this inner parts, okay, by equation actually mean if you set this to 0, okay, that describes the classification boundary that you will get from this particular hypothesis. And what does this boundary look like? You see, you have basically some different scales in each of your axes. Okay, different scales in x1 and x2. That gives you an ellipse rather than a circle. And if, okay, you have, for example, just one of them being positive and the other being negative, then you understand it's a hyperbola. Okay, so basically those are special kinds of degree 2 curves, okay, that's or sometimes called quadratic curves that you can draw on a 2D space. Okay, so by varying the different coefficients, you actually get different boundaries. The circular boundary that we want to use is just one of them, but you can get all kinds of quadratic equations, or even very wild ones. For example, if you set all coefficients to be positive, okay, then as you know, this is a non-negative term, this is a non-negative term. So if all coefficients are positive, your hypothesis would simply always return a positive prediction, which means it always predicts a circle. So there are all kinds of boundaries that you can construct by varying the W or by playing around with different hypotheses. And lines in the Z-space would correspond to special quadratic curves in the X-space. Now, in general, if we consider even bigger quadratic hypothesis set, originally we just take transforms x1 squared and x2 squared, and of course our little old friend, the constant, okay, the x0 or the z0. If we include some other terms, okay, the linear terms x1 and x2, and also the second order cross term x1 times x2, then we can use this to represent arbitrary quadratic hypothesis or arbitrary quadratic curves. Okay, so for example, instead of an ellipse, okay, we can actually have a slightly tilted ellipse. Okay, originally the ellipse we can represent would be like in a normal position. Okay, but now we can have it tilted and so on, and we can also have not just normal hyperbola but tilted ones and so on. So we can represent arbitrary quadratic hypothesis in the X-space. With this, we can now define a new hypothesis set that I call H phi 2. And this particular hypothesis set takes the transform that we have on the top, which is used to transform to a space. Actually, it is a 6+1 dimensional space and do linear boundary there to represent arbitrary quadratic curves in the original space. In terms of mathematical formulation, what we do is to take our x, map it by phi 2 to the Z space, and then use some linear classifier. Okay, in the Z space, okay, the linear classifier would be represented by H tilde here, and that's our hypothesis. And if we collect all those hypotheses together in a hypothesis set, which basically corresponds to all possible quadratic curves you can think about, then, okay, you get a new hypothesis set, H phi 2. And it can implement all possible quadratic curves. For example, if you have an ellipse here with the its equation something like this, okay, if you understand quadratic curve, you will see that this represents that you have one axis for the ellipse and the other axis for the ellipse with some coefficient and so on, and this describes the particular size of the ellipse. That's a quadratic curve. And how can you convert it to a particular W tilde? Well, you just try to collect the corresponding coefficients. For example, okay, let's try some particular coefficients. You have phi 2, the zeroth component of phi 2 corresponding to the constant parts. Where are the constants? You get some constants here by this -4 squared. You get some constants here by -3 squared. And you have this 2 here, so you need something like 2, 3 squared plus 4 squared, and you have a little one here, so -1. Those are the constant parts that you need to have within your W tilde, so you can multiply it with phi 2 to get the value that you want. Okay, so if you calculate that, that will be 18 plus 16 minus 1, that's 33. Okay, so the zeroth component of W will be 33 or negative 33 depending on which part you take. So you can follow this step and get all the coefficients that you want for describing this particular ellipse. And this includes lines and constants as degenerate cases, because lines and constants are simply those W that corresponds to 0 here. If you don't use any quadratic terms, then this quadratic hypothesis set falls back to the linear hypothesis set that we have considered. That's the hypothesis set we're going to use for the very first part of our lecture before we extend it to more complicated hypothesis sets. Okay, so basically not just quadratic, okay, but maybe degree 3, degree 4, or arbitrary degrees and so on. But we will start with the quadratic curves. And now that we know our hypothesis sets, our next question is, how do we get a good hypothesis from this particular hypothesis set? That's the next part of our lecture. But before we do that, let's check if we have some questions on Slido. Okay, good mornings. That's great. Does the final 06 Hangout make some changes from the draft? No, at least not if I can recall. Okay. If I make changes, I'll usually put a note on NTU Cool to indicate those changes. But if you don't see me putting any changes, usually I just putting any notes, then usually I just rename the file to indicate that it's final. Okay, there's an interesting question. Is the transform method 1-1 or onto? If not, doesn't it matter when 2 points are transformed to the same point? That's a good question. Actually, we will revisit the whole flow in the next round, and you will see why it may not matter to us, okay, on whether the transformation is let's call it invertible. Okay, so basically we map to the z space, but true, several points may map to the same z point. For example, actually, in our very first example, we take x1 square and x2 square, and you see that it's basically not you will have some points, actually 4 points, okay, in the x space mapping to the same point in the z space. But it may not matter to us, and we will see in the next part about why. Okay, hello watching peoples. Yeah, we understand that many of you may have some pressure, okay, from your midterms and so on. And for me, I think that's partially the beauty, okay, of this kind of remote or asynchronous learning. Okay, if you can make it, I trust that doing things synchronously with us will give you the best learning performance. But if not, if you have higher priority things to do for now and you want to watch the lectures later, that's fine. Okay, and actually that's a very good way to help you learn to make decisions or prioritize, okay, for your life. And I'm happy that our current digital teaching mechanism allows this kind of flexibility. Okay, can we use rectangle or triangle, even irregular shape of the edge? Okay, that's a very good question. And actually, you will see later that this particular feature transform and then linear learning step can be applied to other cases, not just polynomial feature transform that we're using here. So if you're interested in rectangle or triangle, as long as you can make your rectangle or triangle learning transformed and then linear learning step, you can use this framework. But generally, it may not always be easy. Okay, let me say it. It may not always be easy to only use rectangle or only use triangle. This is much like when we say we want to use circular boundaries. It may not always easy to just use circular boundaries. With this quadratic transform framework that we're using, we're including circular and also ellipse and hyperbola and those quadratic boundaries that we're doing here. So it is possible to use quadratic boundaries. It is not that easy to use only circular boundaries. Similarly, it's possible to design models for example, polynomial boundaries, but it is hard to restrict that we only want to use rectangular boundaries or triangular boundaries and so on, okay? Because sometimes you need some flexibility in terms of describing your hypothesis set. So your learning algorithm, okay, can efficiently pick a hypothesis within. And if you restrict that you really only want rectangle boundaries or triangle boundaries, sometimes it would be harder to design optimization algorithms because you would then fall into more restricted constraint optimization that is generally harder for in terms of designing optimization algorithms. Okay, meta HTML, that's something we can think about for our next generation of coarsening. Can we transform any dimension from X to Z? In general, yes. Okay, of course, we're using a very specific example to describe that we're transforming from a two-dimensional space to a two-dimensional one in our original example, or then a two-dimensional one to a six-dimensional one in our next example. In general, as I highlighted, the steps that we're taking here is flexible. Okay, you can plug in arbitrary transforms and of your interest, and we'll discuss some more transforms later. And when you plug in those transforms, the whole framework should work. How to know the transform function? Yeah, the question I'm waiting for. That's a very good question. In general, we have some transform functions that people are often used that carry some physical meanings and so on. And in some domains, okay, you need some domain knowledge to extract the transform functions to convert your original data to minimal signals. And it is not always easy, and therefore people think about how to automate, okay, the discovery of good transform functions. And one of the successful or at least popular direction for automatically identifying a transform function is the Evo deep learning. Okay, or the benefit of the Evo deep learning is to help us identify a good transform function, or letting the machines learn a good transform function on its own. But of course, we will talk about the cons and pros of this kind of automatically learning a transform function later. In nonlinear transform, whether we just choose 0, 0 as the original point, or we can choose a center after making the transformation. I assume you mean, for example, the circular boundary case. And in the very first case that I described, so basically transforming from a two-dimensional space to a two-dimensional one, I was deliberately using the origin as the center to simplify the problem. Okay, but if you want arbitrary circles or arbitrary circular boundaries, you can use the general transform, which would then include the flexibility to move your circular boundary to arbitrary centers. This is much like in the linear model. When we added x0, okay, and allow us to tune w0, it can represent any line with a different bias, okay, or a different intercept. And similarly, if you want a circle with different origin, you just need to have enough flexibility in your transformation, and then usually you don't need to decide the center. The machines can decide the center or the necessary weights, the necessary combination for you. How do we know whether the data is linear or not? Is it a kind of human learning? That's a very good question that we're going to discuss maybe a little bit later in the class today or early in the class next week. Okay, so basically, it is generally hard, or at least not that feasible to decide whether data is linearly separable or not. But for now, we don't need linear separability. For example, logistic regression can work even if your data is not linearly separable. It can still give you a linear boundary. The price you are paying is maybe you would misclassify some points, but that's fine. So linear separability is not that important to us. But a bigger question is whether linear is good for my data. That's another question. Okay, whether I should just use linear or maybe I should go with this feature transform, that feature transform, and so on. That's the harder question that we're going to answer later about how to use human learning to assist or how not to use human learning to assist, and how to do systematic selection of feature transform or more generally models. Shouldn't the Z-space be linear independent? I assume by independent you mean you want the data to be linear independent. Well, yes and no. Okay, if you care about, for example, separability, okay, of the data, then you may actually want to study some dependence results to see if you can make the proof and so on. Okay, but remember we used the independence argument only for studying the dichotomy, not for the particular dataset, particular label dataset that we have on hand here. And now we have a dataset that's particularly labeled and so on. We may not need to study the dichotomy, the VC dimension, the capacity, and so on. That being said, we care very little about the independence of the or the dependence of the data set that we have on hand. If we use transform function from x to z, can we invert from z to x again? Okay, that was what I answered maybe previously, saying that we may not care that much about z to x, and we will see the reason. And actually, we just presented you with an example that we arguably cannot go from z to x simply because 4 of the same x would map to the same 4 of the different x would map to the same z, and that would essentially mean that we cannot go back from z to x. Okay, great. We have, although some people say that we have not too many people online, but the good thing is we managed to answer many of your very good questions on Slido. Okay, great. Let's move on to the next part. Now, what we have learned so far is we established a correspondence between the z-space and the x-space. Perceptrons in the z-space would mean quadratic hypotheses or quadratic curves in the x-space. A good perceptron would then mean a good quadratic hypothesis. Okay, because if you think about it, a good perceptron, a good H tilde would have the same E in as the quadratic hypothesis in the x-space, the corresponding H in the x-space. And that's what we have established so far. So what we want is to get a good perceptron in the z-space. Okay, that's all. Okay, we know how to transform our data to the z-space. All we need to do is to get a good perceptron in the z-space. And what we know how to do is to get a good perceptron in the x-space with data xn, yn. If you feed the data xn, yn to your perceptron learning algorithm or maybe to your logistic regression, you get a good perceptron. Now, if we want to get a good perceptron in the z-space, what do we do? Simple. You transform your data and then feed the algorithm you have written down, perceptron learning algorithm or logistic regression with z data. You just feed it with z data. That's all. So this is just like you are writing a very basic code to convert your data. Okay, you have one data file, and now you have a particular function that you want to use to convert your data. You write down how to do the conversion, and you get a new data set. You feed the new data set to the algorithm you just written down. Dun-dun! You get a good perceptron in the Z-space. So this is not that hard, okay? To computer science students, this is simply function reuse, right? You have written down a function that can complete a particular task, learning a good perceptron. Now you're coupling this particular function with another function, here the feature transform function, to complete a more sophisticated task. So what do we do here? First step, transform the original data to the Z-space. Okay, that's programmable. Okay, so basically you can, if you know the definition of your file, you can just write down the program and convert your data. Now you get a good perceptron using the algorithm that you have already known in the Z-space. Okay, your favorite linear classification algorithm, perceptron learning algorithm, if you are really old-fashioned, or maybe logistic regression as one of the most popular choices. Now, the issue is here, okay? Remember, what we want to do is testing. Testing means we need to color every point in the space, not just our training examples. So the previous two steps, we're doing it with our training examples. Training examples, transform, and running the algorithm. Now, during testing, what do we need to do? Essentially, we want to get the inverse, right? The inverse mapping, basically, okay? Mapping the particular boundary that we have observed in the Z-space back to the corresponding boundary in the X space. But remember, I mentioned that with the feature transform that we used, phi to the inverse mapping of phi is not always feasible because multiple X points may map to the same Z points. What do we need to do? Well, although we cannot directly do the inverse, remember we mentioned that the phi can be applied to every point in the original space, regardless of whether it's a training example or not. For example, this one is not a training example, but I can still use phi to get it to the Z space, and I get a particular point, okay, maybe something like this here. I can use the perceptron in the Z space to do the classification, knowing that the prediction is blue or circle, and then I can go back to my original space and color blue here. Okay, so I don't really need to go back from Z to X. All I need to do is go from X to Z many more times in order to plot this figure. That's generally what we do. We go from from X to Z many more times. Whenever we get a new example, we go from this new example to the corresponding Z, use the Z space perceptron for classification, and that's our hypothesis. So effectively, what we do is still going from X to Z. We never go from Z to X, or going from Z to X is technically infeasible, but we don't need to go from Z to X. We need to go from X to Z multiple times for every test example that we consider in order to make classification, make predictions for the future. And actually, that's how you see the curves that I have here. Although in this particular case, I can really get the analytic formula for those ellipse curves and so on. But what I actually do is for every grid example that you see in this figure, I go from X to Z. and then gets the corresponding classification from the perceptron that has been just identified by my favorite algorithm and gets the corresponding color, go back, plots the color. Okay, if it's red, it means it's in the negative region in the Z space. If it's blue, it's in the positive region. And if it's black, it means it's very, very near the boundary. So you see the figure. Okay, I didn't actually convert from the Z space to the X space. I always go from the X space to the Z space. That's the basic framework, okay, that we are going to reuse again and again and again for the rest of this semester. There are two choices, okay, in this framework. One, the feature transform that you are considering. And two, the linear model, okay, not just for binary classification, okay, we are using binary classification for illustration here because it's easier to imagine the linear boundary and so on, but you can actually see this kind of steps can be applied to any linear model. If you want to do linear regression, if you want to do multi-class, if you want to do soft classification and so on, you can just change the particular A that you are using here and get the corresponding results. So now you can just do anything quadratic PLA, quadratic regression, and so on. You can do anything cubic, okay, just by changing here to the three-dimensional transform and so on. You can do anything polynomial or even non-polynomial. And of course, in the A part, you can do anything. That's the general framework for nonlinear models in machine learning. And in my opinion, it covers maybe 90% of the machine learning models that you frequently see in the literature. Okay, for 90% or more than 90% of the machine learning models, you can understand them by looking at what kinds of nonlinear transformation it is considering. It is human design, analytic, is it domain knowledge driven, is it automatically discovered, and so on. And what kind of linear model is being coupled with this nonlinear transform? Is it the very fundamental logistic regression, or maybe some extensions to multi-class classification and so on? And I'm saying this is a Pandora's box, okay? What do I mean by Pandora's box? It gives you lots and lots and lots of possibilities, okay? But you will see a little bit later that it can cause some negative effects too, okay? Some evil, okay, in some sense. And we will see why in a few moments. For one, some of you ask, okay, now it seems that we have lots of choices. Okay, I can have transform 1, transform 2, transform 3. I can have linear model 1, linear model 2, linear model 3. How do I choose which one to use? Okay, it seems that there are lots of possibilities, but no one knows how to choose it. That's not helpful, and we need to discuss that a little bit later. Now, feature transform is not that new to us. Okay, if you recall, in the very beginning of the lecture, we mentioned that in a particular data set of recognizing handwritten digits, one way of representing the data is to use pixels. But we mentioned that pixels carry very little physical meaning and so on, and therefore you may want to transform it to a more meaningful space before running the algorithm. And originally we talked about one particular transform that's human designed using symmetry and intensity. Okay, then we can use that to classify one versus not one. That's one particular binary classification problem in the one versus all model. So we're transforming raw pixels, okay, to concrete features with domain knowledge. And that's another feature transform. It's not a polynomial transform. You see how domain knowledge helps feature transform and so on. And of course, in terms of this optical character recognition problem, nowadays, the modern way is to use deep learning. Some of you may have heard of convolutional neural network to automatically learn the transform rather than using the domain knowledge. But the idea is similar. Okay, you have a model that includes the transform part, the linear and the linear model part. And during testing, you are reusing the particular transform and the linear boundary that you have learned from your algorithm to do classification or to do prediction. Okay, and I often call this the force. Okay, if you know Star Wars, you will know that the force is arguably the most powerful thing in the universe and so on. But of course, there are the bright side of the force and the dark side of the force and so on. And what we are going to discuss a little bit more next is the dark side. Okay, it's powerful, but if you use it to do evil, lots of bad things can happen, and we will see why in a few moments. But before we do that, let's see if we have some questions on Slido. Does VC dimension hold in Z space? Generally, yes. Okay, but we will discuss a little bit more about this later. Basically, the yes comes with some assumptions or some principles you need to follow. For example, you need to design the transform without looking at the data. Okay, if you design the transform after looking at the data, then other parts of, for example, your smart brain would go into the game, and VC analysis would not work in the Z space. But if you truly design the transform without looking at the data, then I mean, you are effectively just doing analysis in a new space and so on, and all the VC theory would work there. What if we can't find a transform function that Z is linear separable? Is there always a transform function that makes the problem linear separable? That's a very interesting question, actually. Okay, in short, for every data set, there are transforms that makes the data set linearly separable, and it's not that hard to find, actually. Okay, provably, for example, if you are using a polynomial transform like what we have described, and your polynomial is of higher order than the amount of data that you have. Amount of data roughly it is roughly related to n, big N, okay, where big N is your number of examples. Then you are guaranteed to make the dataset linearly separable. Okay? This is much like in our previous question when people ask whether the VC analysis hold, and I said yes. And if you think about it, if the VC analysis hold, it actually means the powerfulness of the perceptron hypothesis set holds. The perceptron hypothesis set says, okay, there's a particular VC dimension of the perceptrons, and above the VC dimension, in general, okay, if you have examples that are in general position, not collinear and so on, you can produce an arbitrary dichotomy on those examples. And when you can produce an arbitrary dichotomy, generally you can show that you get something linear separable. So even when just using polynomial transform, as long as you have a higher order polynomial transform, based on the result of perceptrons, you can prove that things are linear separable. But as we will see next, linear separability, although we use it as a motivation, is generally not that important. What we care about is not linear separability. Okay, insisting things to be separable does not always make learning better. Okay, but what we care about is to use feature transform to have a bunch of different machine learning models that are tunable in terms of VC dimension, so that we can get the best trade-off between complexity and generalization. Okay, so in that sense, we usually or almost always don't care about whether things are linear separable. Okay, if things are not, It's fine. Most algorithms, except for maybe PLA, can handle non-separability well. And what we want to do is not pure separability, okay, but a better representation that we can tune with to get the best performance. Can we do the transform of a transform? What will it be like? Okay, that's a very interesting question. And the short answer is yes. Okay, if you think about it, if you couple a quadratic transform with a quadratic transform, okay, so this is the typical technique of function composition. If you couple two quadratic transforms together, you are effectively getting a fourth order polynomial transform. So technically, it's possible. Okay, you can do anything. Okay, that's why we call it Pandora's box. Okay, so if you ask me whether we can do this in this framework, I'll always say yes. Okay, but the important thing is to understand the trade-off. Okay, what's happening? Okay, after doing the transform, what's the price we are paying when using a transform or another layer of transform? And actually, if you think about deep learning, although we haven't formally taught deep learning yet, one famous thing about deep learning, the reason that deep learning is called deep, is deep learning can be decomposed to layers, and each layer corresponds to a feature transform. And if you go to the next layer, you are having a feature transform on top of the original feature transform. And therefore, if you look at deep learning, for example, with 100 layers, it's basically combining 100 transforms all together and so on. So that's certainly possible. Okay, the important thing is to notice that there's a price that you need to pay when you do this. What if there are some noise in data affects our transform function? Okay, when there's noise in data, it's generally that's just noise in data. Your transform function, if you are making it higher dimensional and so on, it can emphasize those kind of noise. And the transform function itself will not be affected. Transform function is just there. It's there to help everyone. But if the transform function emphasizes the noise, okay, because transform function is just like signal processing in some sense. When you have noise in your signal and your transform function emphasizes it, okay, then your learning algorithm can be affected. On the other hand, the transform function may not always emphasize the noise. If you think about the case where we're converting pixels to more concrete representations, you can actually imagine that the transform function is reducing noise, reducing feature noise in some sense. Okay, so for example, if you have a very little stain in your OCR when you write down a character and so on, and you apply a transform function of symmetry and intensity, okay, the stain may affect the intensity a bit, the symmetry a bit, but generally not too much. So transform function does not always emphasize the noise. Okay, sometimes it can decrease the noise as well. And usually the more important thing is whether your algorithm is robust enough to the noise. Is feature transformation equivalent to polynomial kernel? Okay, that's a topic we are going to teach later in kernel machines or kernel methods. The short answer for those who know the kernel methods now is that the polynomial transform is embedded within the polynomial kernel. Okay, so but there are some subtle differences that we need to discuss later to establish the equivalence or the particular embedding. Can we open the function of reply or dislike in Slido so we can answer others' cues directly? Okay, that's a very good suggestion. Let me study how to do that. Okay, we may need some I don't know, the particular features of Slido, maybe paid or so on. And if we can do that, we will consider that. Thank you. Okay, great. Now we have answered all questions and coupled some of these feature transform routes that we want to cover. Let's take a 10-minute break before we continue with the next part of the lecture. Okay, welcome back. Let's continue our lecture here. Okay, so we talked about the polynomial transform starting from the quadratic or degree 2 polynomial transform. And we can actually define the polynomial transforms in general, okay, to the cube order, okay, to the cube degree. So basically, this is the first order part. Okay, so basically that corresponds to the original linear part. And we have our old friend, this little constant here, that was x0, or now also z0 as well. But we can include more transforms, for example, all the quadratic terms. Okay, that gives us a second order transform, and up to all the cube order terms. Now, this is the general cube order transform containing all the possible terms that you can possibly think of within the order of Q, and also for general d-dimensional x vectors, or 1 plus d-dimensional, where the 1 is just the constant term. Now, the dimension of this particular transform is this 1, okay, which represents w tilde 0, and then d tilde, okay, d tilde are those added terms. Now, this d tilde actually, 1 plus d tilde actually represents the number of ways to get combination from d kind with repetitions. D kinds meaning there are d different original features in X, okay? And from those d kind, okay, if you are choosing with repetition to get Q or up to Q items, okay, that's the typical number in combinatorics that you may want to calculate. For those speaking Mandarin, 重复组合。所以你在这边其实是在算一个重复组合的数量，说这个 dimension 到底有多大。So we're calculating combination with repetitions, okay, and choosing from the original values and see how many different kind of combinations that we can make for up to Q dimensions. If you go to your discrete math class or combinatorics class and see what the number is, okay, it's generally just Q plus D, choose Q. Okay, that's a typical result that we're not going into the details here. And you don't need to know this exact number, okay? You just need to know in terms of roughly representing it's about Q to the D degree. Okay, so if you're doing a 10th order polynomial transform on 5 dimensions, then this particular vector is roughly of length 10 to the 5. Okay, roughly, of course, not exactly and so on. As you can see, that's a very, very big number. Okay, and with this big number, it actually means we need to spend this big number of computation. Every transform that you are using needs this kind of computation, right? Okay, you have x, and every time you are calculating phi of x, you are paying for Q to the D. And also, the length of your weight vector is of this particular length as well. It's of length d tilde as well. So you need this length to store your w tilde, or possibly also to store all the z's that you have computed in your memory. So for one thing, there are computational and storage overheads for using high-dimensional polynomial transforms or high-dimensional feature transforms in general. Okay, if your dimension is higher, you pay for more computation and storage. That's one bottleneck we typically need to check when we want to use high-dimensional transforms. And the other important price that we need to pay is the model complexity price, because Now we are running a perceptron in this super high dimensional space. We are paying for the perceptron complexity in this super high dimensional space. The number of free parameters in that space, d delta plus 1. And as we mentioned, okay, this is roughly the VC dimension that we need to consider. Therefore, if you don't have enough examples, this huge number may cause you to not have any guarantee from the VC part. And you can actually prove, we're not going into the details of this lecture, that the VC dimension would always be less than or equal to d delta plus 1, okay, because of the mapping here. But I'm not going into the details here. You can think about that as your own exercise. But anyway, okay, although this is just an upper bound results, it actually tells us that if we use a higher dimensional, higher order polynomial transform, we are paying for a larger VC dimension. And large VC dimension is not always good, as we have learned from the VC theory. And with this huge model complexity we are paying, there may be some interesting results. For example, in this particular data set that we consider here, you may be interested in just using phi1. Knowing that the dataset is not linearly separable, and when using phi1, you need to pay for some errors, like here or here. Those are the errors that you need to pay for using a linear model. Or you can use another transform, phi4. Okay, basically saying, let's convert all our data to a higher dimensional space, and this particular higher dimensional space would then, in that higher dimensional space, things are linearly separable. Then when you map this higher dimensional space back to the original space, this is the particular boundary that you will get. And this is a fourth order boundary. It classifies every example correctly, every original example that you have seen correctly. So now the question we want to ask, and I have actually announced it on Slido, okay? Which one do you prefer? Do you prefer phi1 or do you prefer phi4? Phi4, no error, complicated boundary. Phi1, some error, simple boundary. Which one do you prefer? Okay, let's give yourself a minute, okay, before we continue with the discussion. Okay, our result shows that phi1 gets 88%, nearly 87%. 87%不能再高了. Okay, I just have to tell a Mandarin joke and so on. Okay, but anyway, okay, many of you seem to prefer phi1. Okay, possibly because of the simplicity that you have witnessed, or you believe that trading, okay, the simplicity for powerfulness, okay, is kind of helpful. Okay, you can perhaps believe that the two examples, that the two errors you have to make with the linear model is not such a bad idea. Okay, and while using 5-4 may be an overkill. Of course, for people choosing 5-4, there's no right or wrong. Okay, when you choose 5-4, you actually believe that maybe the 5-4 boundary is somewhat meaningful. Okay, at least maybe for the part where you have a particular cluster of those circles, maybe those parts are meaningful by itself, and the transform helps you capture it. There's no right or wrong, okay? But the visually preferred one in our previous experience is indeed usually 5-1. 5-4 has sometimes people believe it to be an overkill simply because they don't like the very curvy boundary that 5-4 represents. Okay, so that's the typical results that we see, but the more general question that we want to discuss is, sorry, let me switch the window. If you look at the question that we have discussed about how machine learning works, this actually corresponds to the dilemma that we're facing with the two questions in machine learning. We want E in to be close to E out, and we want E in to be small. When using 5-4, okay, we're basically doing better in terms of the second question. Okay, basically making E in small enough or as small as possible. If we use a higher d delta or a higher Q or higher order transform, we get something like better for question number 2. But not question number 1, because we pay for a higher price in generalization. On the other hand, if we use a lower dimensional feature transform, we are doing better for question number 1, but possibly not too good for question number 2. That's the trade-off. Okay, so the question we've asked you to check is just representing this trade-off. Okay, there's no right or wrong in terms of choosing 5-1 or 5-4. There are of course subjective preferences from human. Okay, but there's no right or wrong. Now the question is, how do we pick? In this particular case, it seems that we deliberately ask you to pick visually. But is it a good idea to pick visually or not? Let's think about it. For one thing, can you really visualize when your original data is in a 10-dimensional space? Currently, we give you data sets that are 2-dimensional, and in 2-dimensional, we human beings can kind of visually analyze what's happening and make some decisions and so on. Or maybe in 3-dimensional, some people can do that. But let's say if you have data in a 10-dimensional space, a 100-dimensional space, or dimension 1126, can you really visualize what's happening there? Well, at least I cannot. Okay, I don't know if anyone can, but I cannot. Visualizing in a high-dimensional space is hard. Therefore, if you want to apply machine learning in general, it may be hard to do model selection or feature transform selection visually. That's not a good idea in general. And also, when we do, even if we can do it visually, it can be dangerous to pick feature transforms visually. Why is that? Let's think about this. Okay, we have introduced several feature transforms so far. Okay, if we use a full phi2, the VC dimension that we're paying in this case is 5 plus 1, which is 6. If we do a visual analysis of this data set and decide that no, we don't need a full phi2, we just need a feature transform that's centered at the origin, then what we can do after visualizing is decrease the VC dimension we're paying from 6 to 3. because we just need a 3-dimensional feature transform rather than a 6-dimensional feature transform if we use our visual analysis to decide that we only need a simpler feature transform. Wow, that's so cool. We seem to be using our human intelligence to save the complexity we need to pay in terms of the VC price. But is that good? If we can really do visual analysis, what I can do even better is to say, I don't need to use ellipse. I can just use circle. If I just want to use circle, I just need a 2-dimensional feature transform, not a 3-dimensional one. The 2-dimensional, including a constant transform, is just calculating the distance to the origin. By using this feature transform, I'm just paying for VC dimension of 2 after visualizing further. Oh, cool. You are decreasing from VC dimension 6 to VC dimension 3 to VC dimension 2. Can we do with VC dimensional 1? Sure. How about we just use a feature transform that includes the answer? Okay, so you use human analysis, you draw a circle, you measure that the circle is of radius 0.6, and therefore you write down that the feature transform you want to use is sine of blah blah blah, the circle you just draw. That's a 1-dimensional transform. Therefore, you seem to be paying that the VC price of dVC equal to 1. Okay. Hopefully you feel a little bit suspicious about this. Okay, this kind of thing doesn't come for free. You seem to be decreasing the VC dimension that the machine is paying. But now another complexity that cannot be formally described under mathematical terms is getting into the play. What if your brain's model complexity is too high? Remember, if you can do all this, you do not necessarily need to use your brain to draw a circular boundary. You can use your brain to draw a boundary like maybe this. Okay, I'm deliberately drawing it in a very ugly manner. That's also possible with your brain. That's also possible to describe this as a 1-dimensional feature transform that's perfectly linearly separable with a VC dimension of simply 1 because you are just encoding the decision boundary generated by your brain. But you are cheating when you do this because although it appears that the machines don't know about this and the machines can just pay a price of VC dimension 1, you need to pay for another price, your brain's model complexity. Although your brain's model complexity cannot be described with very clear mathematical terms, you should know philosophically that it's there. For example, when you use a super complicated boundary like what I draw to describe your problem, then this is the huge price you are paying because this particular boundary may be overly sensitive to the data that you observed and so on, or in VC terms, the boundary will not generalize well. It is hard for you to guarantee that E out is close to E in with the boundary generated by your head. So this is the message for you. We are visualizing here, and we can, of course, use our visualization to generate the boundary. But when you visualize, your brain's model complexity gets into the game. And when it gets into the game, it can be nasty. Because, okay, come on, it is hard to quantify the amount of complexity you are paying with your brain and so on. And therefore, whatever results after you visualize the data and get into play is kind of contaminated by your brain's complexity. We'll discuss more about this later, and this is not just for visualization. It actually applies to every step you do analysis with your data. We often do analysis with our data before running the machine learning model and so on, but now I want to hint you that there's a price that you may need to pay, much like the price you need to pay when doing visualization. You use the data for analysis, for visualization. Your brain thinking get into the game. You need to pay some price in terms of generalization for that, and that may affect how your eventual machine learning model generalizes to unseen examples. Now, if you really want absolute VC safety, meaning you want the whole VC analysis to be useful for machine learning only. Then you need to be very careful, because you generally need to prevent your brain's complexity from getting into the game. Okay, you should not pick the data before deciding your transformation. We will discuss later that this is very, very hard. Okay, it is very hard to close your eyes, not looking at any data, and throw a machine learning model, and bang, your result is successful. No, it is very hard to do so. So typically, you need to balance. You need to know that it is dangerous to do so, but on the other hand, you cannot prevent doing so 100%. But now, let's be a little bit more idealistic. Ideally, you should choose the transform without looking at the data. Okay, that's the ideal suggestion we give for now. And we will loosen this suggestion a little bit later when we discuss about practical machine learning in maybe the next class. Questions? Okay, there's a question in Mandarin. Let me translate it. Okay. We discussed about the computation and storage costs for feature transforms and so on. And the question is, does this mean that machine learning is a capital war? And in terms of it may need lots of computation, for example, paying in transformation, paying in algorithms, and so on. And for people not having enough resources, we cannot beat companies with lots of resources like Google, Facebook, and so on. And if we don't have the resources, then maybe we will always fall behind and so on. That's a very interesting question. In terms of research, okay, let's say research is something with lots of flexibility. Okay, so there are questions where you really need lots of resources to learn well, and resources, not just computational resources, for example, data collection resources and so on. And yes, those needs money and so on. If you want to work on those problems, true, okay, you need lots of resources, and it's best that you go to somewhere with those resources to do well. On the other hand, there are problems where you don't need that many resources, or there are problems that deliberately focus on the situations where things are resource limited. For example, if you study machine learning on mobile devices, okay, the computation on mobile devices is limited. The power on mobile devices may be limited. The storage on mobile devices are limited. And in those areas, okay, whether you have lots of resources is or may not be the main bottleneck. Okay, and whether you have good ideas can be more important. So what I say to, for example, my lab students is that we pick the right problem. Okay, we don't pick the problems that are infeasible to us. We pick the feasible problems, we try to work hard under the resource constraints that we have, and we try to solve it properly. And this doesn't only apply to research. Actually, if you think about it in industry settings, there are also companies with lots and lots and lots of resources. Okay, like bigger companies, for example, Google or Alphabet or Meta or whatever. Okay. But on the other hand, there are, for example, startup companies that do not have that much resource, but they still need to differentiate their strength and so on. And actually, in company settings, not just computing resources, but for example, there are resources like time. Okay, the timeline is typically very tight. Okay, in startup companies and so on. And what we typically do is to treat it as constraint optimization problem. True, resources are constrained. And what we need to do professionally is what's the best we can do under the resource constraints. That applies everywhere. And I mean, okay, the fact that many other places have lots more resources and so on, it simply means they can solve the problems in a little bit less constrained way. Okay, but actually, one thing amazing about machine learning is we keep solving problems under constraints, computational constraints, storage constraints, production constraints, timeline constraints, and so on. And that's fine. Okay, the universe is big enough to include all those kind of problems. Okay, complicated bounds may lead to overfitting. Okay, thanks for hinting that, and that's the next topic we're going to talk about very soon today. In Z space, okay, can we use this dimension? If you pick a transform that's decided before you look at the data, then the Z space is just another representation with your data, and everything that we learned about VC theory can be applied to the Z space. Okay, phi 1. Okay, and thank you for giving us reasons about why you think phi 1 is better and why phi 4 may be the actual answer. And actually, the important thing about using phi 1 or phi 4 is we don't know. We don't know which one is the one God used to generate the data on hand. Okay, remember, machine learning is doing reverse engineering and so on. We don't know what the original engineer, or maybe God, used when generating the data, and therefore we're just playing with the dilemma. Okay, we may not always know what the truth is. Okay, why okay, we want to seriously ask you to be respectful to every member and so on. We cannot allow attacking wording, okay, on Slido. And I try my best to, with my translation ability, of course, okay, to help translate. And so hopefully, okay, all language speaking students can get their answer and so on. And there's really no need to attack other people. Okay, is this the concept of PCA? Okay, and I'm assuming you are saying PCA as principal component analysis, and actually you can view principal component analysis as a kind of feature transform, but not the kind of feature transform that we're mapping to a higher dimensional space, but sometimes we're mapping to a lower dimensional space by PCA, this particular technique. Okay, if you don't know what the technique is, it's fine. Okay, you just think of it as derived a transform function that's mapping to a lower dimensional space. And yes, when mapping to a lower dimensional space, then you can say that the dimension that you're paying for machine learning is lower. Then you need to pay for the complexity, okay, that's that are associated with the PCA process, much like we paid for the complexity price in our brain. So every processing step, your brain, PCA, any feature transform you choose, and so on, has a price. And as a professional machine learning learner, what we need to do is really to know the price we're paying, or at least to have a feeling of the price we're paying to choose the best model that we're going to use. Okay, great. let's see. And in terms of the polynomial transform, actually we can revisit what we have learned so far and see that originally we have phi 1 being the linear transform, or the original transform that we have used. We can even go one level lower, defining phi 0 as the constant transform, the x0 that we have been using since literature 1. And then you see that phi 2, okay, we can use a recursive definition, having phi 2 starting with phi 1, adding all the degree 2 terms. Phi 3 being phi 2, adding all the cubic terms, and so on. Okay, so with this definition, we actually mentioned that then you can view some special cases within your hypothesis set H phi 2 to be just including H phi 1. Because given that phi 2 just adds all those features, if we set the weights on those features to 0, we just fall back to using phi 1, which means we're just falling back to H of phi 1. That is, in terms of hypothesis sets, we can imagine H of phi 0 to be included in H of phi 1 to be included, and so on. And this inclusion relationship allows us to draw the hypothesis set this way. And I'm simplifying this notation to H0, H1, H2, and so on, so we don't need to look at the ugly phi again and again. And this kind of nested hypothesis set is usually called a structure hypothesis set. Okay, so there's a structure within your hypothesis set. Why is this structure important? Because this structure actually tells us two things. One, in terms of the VC dimension, when we have more and more and more hypotheses, the VC dimension goes larger. You can shatter more examples, and therefore the VC dimension goes larger, goes higher. Now, in terms of E in, when you have more hypotheses and you are minimizing E in over your hypothesis sets, then E in goes lower. You have more choices, right? Okay, when you have more choices, either the new choice is of lower E in and you pick that, or the choice is not of lower E in and you stick with the original one. But anyway, you generally just have a non-increasing relationship. And then remember our figure here, model complexity grows. In sample error decreases when you increase the VC dimension. And in terms of out of sample error, something in the middle is the best. Not something in the left, not something in the right, something in the middle. That is when you start with a super high dimensional feature transform, like H1126, somewhere here, definitely it will not be good. Okay, so although 1126 is a lucky number, it's not good to start from this side. This should distinguish you from typical amateurs of machine learning. For amateurs of machine learning, it's usually very tempting to start with a really complicated model and then get a low E in and tell your boss, hey, on the data that I have on hand, I get a very low E in. Yeah, I succeed. But actually, you are in this region. You get a low E in, but you were out of sample error. The E outs that you really care may be very, very bad. This is fooling your boss, and this is fooling yourself. And this is not safe. What can we do? Well, what we can do is to start from the left, using a simple hypothesis first. If your simple hypothesis already do well, good. You live happily thereafter, like magic story and so on. If it is not good enough, you move to the right. You pay for some additional price, okay, much like in the structure hypothesis. You start from H1. If H1 is not good, you go to H2. You pay for a slightly bigger price, okay? And because H2 includes H1, the price that you pay for H1 is already there, okay? You pay just for the difference, okay? You don't pay for new prices and so on. You have very little to lose, okay? You either get better or gets worse, okay? But, sorry, you will get no worse than what you have started with, okay? So that's the safer route, to start from the simpler model first, or in our case, the simpler model is actually the linear model. So this actually also explains why we teach you the linear model first. We want you to use the linear model first. It's simple, it's efficient, it's safer to start from the left to the right, and it's workable. If you go to the industry setting, actually with some good feature transform that were predefined by the domain knowledge during the data collection process, linear model can often already do pretty well, pretty suitable for many of the production settings. You don't need much more than the linear model. In this case, we encourage you to start from the linear model, start from the simpler model, so you can use machine learning more safely. This is much like what? When you use fire, okay? So fire is important, fire is powerful, okay? But you really don't want the fire to burn your house, so you want to use fire under control. And what we mean by under control is really start from learning to use basically little fire. And then grow a bit, and then grow a bit. Always put your fire under control. Similarly, for machine learning, always put your model complexity under control, starting from the left. That's the safer route you should use. Okay, questions. No questions. Great. Okay, let's start another 10-minute break before we continue with the next part. Thank you. Okay, so after knowing about the transforms, in particular higher order polynomial transforms, we now have the tools to study one very important phenomenon in machine learning called overfitting. And previously, outside this class, you may heard that overfitting is caused by for example, excessive complexity. You can imagine that when you are using a more complicated boundary and so on, or higher order transform, you have a better chance of overfitting and everything. We're going to into more details. Okay, you will actually see that there are more issues that are related to overfitting, and knowing those issues from a more general angle actually helps you use machine learning better in your future projects. That's what we're going to do in the next part. Okay. Now, we know about using higher order polynomial transformation, and now let's apply it to a particular case of regression. Now we can do polynomial regression, not just classification. We can do regression. What we're going to do is to generate 5 examples and generate those 5 examples from a target function that I marked in blue here. That's a second order polynomial. Okay, so you see that all those 5 examples are come from just randomly sample x and evaluating the corresponding y, but we add some very small noise. Okay, so you see that those points are not exactly on the blue curve, okay, but a little bit different from that. Okay, for example, if you see this point, okay, this difference between the circle and the blue curve is the noise that we're considering. Now with this data, okay, 5 examples and 5 labels containing very small noise, we do linear regression with a 4th order polynomial. We have 5 points. If you use a 4th order polynomial, you will be able to pass all examples exactly. That is, you will get the red curve with E in equal to 0, exactly 0. If you run a 4th order polynomial regression on the problem. And as you can see, E out. What is E out here? E out is the difference between your red curve and the blue curve. Blue is your target, red is the hypothesis that you get, and the difference is E out. E out is huge. The red curve is very different from the blue one. That's called bad generalization. We have low E in, very low, 0 E in, but high E out, okay? Now, if we take a hypothesis set with a very high VC dimension, much like we take a 4th order polynomial in our previous case, or maybe let's exaggerate it and use an even bigger number of 1126, then there's bad generalization. E out minus E in can be large. That's what VC tells us. VC tells us if you use a super high VC dimension, there's bad generalization. If you switch from the good VC dimension to a much higher one, okay, switch from the good one to a much higher one, that's generally called overfitting. Why is it called overfitting? We are fitting, we get lower E in. That's fitting. Okay, fitting the data that we have on hand. But we do it too much, too over, so we get a bad E out. So one simple definition of overfitting is we get a low E in, a high E out. Okay, so it is not just E out being large, in being small. It is the kind of the process or the comparison between the optimal case and the current VC dimension that we're paying. So overfitting is kind of comparing to a baseline or to the idealistically optimal case. Okay, how well we are doing. Okay, we are fitting too much. We are overfitting. That is, this region here is the overfitting region. On the other hand, if we are looking at the other region, that is the left-hand side. This particular left-hand side region is generally called underfitting. We want to do some fitting, but we are not doing it well enough. We are underperforming. We are not fitting well enough. That also causes worse E out. That also causes higher E out. But the higher E out is because we haven't fitted, we haven't made our E in well enough. That's underfitting. Knowing which region you are in is very important for tuning machine learning models, because if you are in the overfitting region, you generally need techniques that brings you back to the sweet spot. On the other hand, if you are in the underfitting region, much like when we encouraged you to start with simple models, then you need to increase your model complexity to get to a better point. So knowing which region you are in is important, and we will see later when we look at other machine learning algorithms. Batch generation, low E in, high E out. Overfitting, lower E in, higher E out. And that's what we're going to discuss. And actually, overfitting easily happens in machine learning. That's why people paid much more attention on overfitting or overfitting prevention or combating overfitting, like what we're going to talk about next. People paid much more attention to that. To combat overfitting, we first need to understand the cause of overfitting. And I'm going to use a driving analogy to help you understand that. Now, a good fit that we want to have is to have the red curve, that's the learned hypothesis, to be close to the target function, the blue curve. That's the good fit. But when we overfit, okay, we seem to have lower E in, very low E in, but higher E out. What's the possible cause? Now, the analogy is that overfitting is like committing a car accident when you drive. What's the possible cause of a car accident? Well, if you have excessive power, it's much like you are driving too fast. When you drive too fast, it increases the risk of getting a car accident. When you have enough power to basically, for example, making very, very low E in, or in the VC sense, generate every possible dichotomy and so on, okay, it seems to be a possible cause of overfitting. But there are also other causes as well. For example, the important thing that we want to highlight here is that noise plays a role. Remember, in our original data set, we added noise. If there is no noise, okay, if our example do not deviate from the blue curve, then even when we are using a 4-dimensional curve, it is possible that we get a curve that falls back to something very close to the blue curve. But when we have noise, noise gets emphasized by the excessive VC dimension. Noise gets emphasized by driving too fast. Noise is like what? Like the bumpy road. Okay, when you have little stones on the road and so on, and you drive very, very fast, okay, then the little stone can cause your car to be less stable, and then a car accident may happen. So noise is like bumpy road. When the road is super smooth and so on, arguably you can drive fast or a little bit faster and not causing much risk for car accident. But when the road is bumpy, then driving too fast can be a problem. So noise is a possible cause of overfitting, and actually noise is almost everywhere in every possible real-world data that you collect, and therefore it is very important to know that noise is a cause of overfitting as well. And not just noise. In machine learning, we always just have limited data. Limited data is much like when we are driving, we only have limited observations about the road condition. Right? Okay, we are human beings, we watch the road condition and so on. But if you only have limited observations, then, for example, you cannot see clearly where the road is bumpy. And therefore, when you also drive too fast, then car accidents happen. If you have infinite amount of data, okay, then even if you have some noise, maybe it's fine because the infinite number of data would, in the figure above, maybe just cover every possible parts of the blue curve. So even if you are using a 4-dimensional curve or a high-dimensional curve, you can kind of approximate, okay, through those very, very dense data correctly. But if you only have limited data, the VC theory tells you, okay, we can easily generate all kinds of dichotomies and so on. Or basically, we pay a lot in terms of the generalization price, the model complexity. Limited observations is another cause of overfitting. And the next thing that we're going to study is how this exactly affects overfitting. We are going to use some artificial examples, okay, some artificial cases to simulate, okay, the actual overfitting that you may observe in practice. Okay, given that I see there are no questions, let's just continue with our case study here. The first part of our case study would be on, okay, a 10th order target function plus noise. Okay, so we are making things a little bit more complicated than before. We have target function, 10th order polynomial, that's the blue curve, and plus noise. So you see that our regression data are not exactly on the target function. Okay, they can be very different from the target function. And also, we consider a noiseless case, okay, where we have a 50th order target function, very, very complicated target function. We'll use that to generate data, but we don't add additional noise. The purpose for doing this is really understanding, okay, the interplay between target and noise. Okay, so complicated target, no noise. Slightly less complicated target, some noise. And we'll see what happens when we use two particular models. H2, second order polynomial transform. H10, 10th order polynomial transform. Now, before we start with anything, okay, you can imagine that at least for the case on the left-hand side, 10th order polynomial matches the target function more. Second order polynomial, H2, may be not powerful enough for the 10th order target function we're considering. Okay, so it may seem that using the green one, using H2, is doomed to fail. But we're studying the overfitting effect anyway, and it will show us something interesting. By overfitting, we're going to study what happens between H2 and H10, or what happens when we move from H2 to H10. Is there overfitting? When we move from H2 to H10, E-in must be better. So when we say whether there's overfitting, we ask whether E-out becomes worse, whether E-out becomes higher. Okay, let's see the result, left-hand side. When we move from H2 to H10, E-in is lower, from 0.05 to 0.034. Very good. E-in is lower, that's as expected. And the H2 curve that we found is this green one. Okay, so that's how we evaluate E-in and E-out with. The curve we found from our 10th order polynomial is this red one. So moving from green to red, E-in gets lower, but E-out gets much higher from 0.12 to 9. Much, much higher. So the 10th order polynomial that we get is very different from the target function we want. target function, the blue one here, and the 10th order polynomial, a very curvy red curve that's very different from the blue one. So when there is noise, even if we're using the right model meaning the model containing the target function, it seems that we will encounter overfitting because of noise. Okay, we're using the right model, but when there's noise kind of leads our optimization away, or leads our machine learning away. So right model, right meaning the model that contains our hypothesis does not always guarantee learning well, because the power of this particular model is used to fit the noise, not the true signal, not the true pattern that we want to capture. How about the left-hand side? You say, okay, the right-hand side. In the right-hand side, there's no noise. Are things better? There's no noise, but we're using a 50th order target function when we're moving from G2 to G10. Okay, again, E in always lower as expected, but E out very good or somewhat good when we're using a second order polynomial, but very bad, I mean even worse than the previous case for G10. Okay, that's nearly 8,000, and I'm not typing the wrong number. You see, again, we get a very, very different curve compared to the blue curve that we want to approximate here. Okay, so in both cases, overfitting happened. Overfitting from G2 to G10. Yes, E in gets lower, E out gets higher, actually much higher. So the message that we see here is that in both cases, we have an overfitting learner that picks G10. We have a very restricted learner that picks G2. Okay, restricted, constraining itself to say, no, I'm only using second order polynomial. I'm not going into the 10th order. That's way too dangerous, and so on. And in this particular case, they both know that the target function is 10th order, or at least we know. But even if we know the target function is 10th order, even if we're choosing the right model for the target function, we cannot do well. The learner R, the restricted one, actually gives us the ability to fit, but eventually it does better in E in. This is called concession for advantage. In Mandarin, 以退为进. Okay, it seems that when we constrain ourselves, we're able to do better. We're able to prevent overfitting in some sense. And this is an important message. The important message is we are not picking the model according to whatever our imagined target complexity. Because even if you know the very right target complexity, the noise or your data size can also cause you to overfit. In machine learning, it is not always that important to pick the correct model. Correct model meaning the one that contains your target function. It is important to pick a model that achieves low E out. And when you want to achieve low E out, it can be important to give up on the correct model. Use a more conservative model, use a more restricted model to eventually get a better E out. That's the philosophical message that we want to tell you through this very illustrative case study. And why is that? If you look at the learning curve that we quickly introduced during linear regression, we can also plot the learning curves for H2 and H10. Remember, the learning curve contains on the horizontal axis and the number of examples you're considering, and the vertical axis, the arrow E in and E out. When you have infinite number of examples, in and E out would be very, very close to each other. But we're not talking about infinite number examples. We're talking about a finite number of examples. Okay, so in a sense, we're in the gray area where E in and E out could be different. Now, this is the curve of H2. What would the curve of H10 look like? It would look like the right-hand side. Eventually, things are lower. Right? Okay, eventually you can get lots of points and so on converging to the right place, and with more examples and so on. So eventually H10 is more powerful. The error, the converging error is lower. But when you have a smaller number of examples, the difference between E in and E out can be high because there's a much higher complexity price to be paid. So if you look at the gray area, if you want a lower E out, which one should you pick? H2. H2 gives you a much lower error in terms of E out than H10. H10 is eventually helpful only if you have enough examples. But if you don't have enough examples in the gray area, learner O, the learner who insisted on using H10, overfits. E in gets lower, E out gets higher. And when your number of examples is small, it's best to be restricted. So I'm hoping this case study convinced you two things. Noise, okay, which is the secret ingredient that we injected to the process to cause the overfitting, and the limited number of examples. Both are important, also important, okay, in addition to the excessive power for causing overfitting. Overfitting is not just caused by excessive power. It's caused by excessive power and noise and limited data. Now, you say, but there are cases that doesn't seem to contain any noise, right? We use the 50-degree polynomial as our target function without any noise. Why is there still overfitting in this case? Well, when there's no noise, but our target function is by itself higher dimensional, think about it. For both H10 and H2, they are far from perfect. When they are far from perfect, then the difference, okay, between what can be modeled and what we want to model can act as noise. And this is typically called the target complexity. Okay, this is not the complexity of the model you choose to use. This is the complexity of the function you want to learn. If you want to learn a really complicated function and your model cannot capture that complicated function completely, then the difference becomes like noise. That is, okay, when we see the 50-order polynomial here, we see that the points are kind of jumping up and down. And when things are jumping up and down, it is very hard to model, and those act like noise. And let me switch to, a later slide that may illustrate this a little bit better for you. You have a target function of f. You have the best hypothesis that can be captured by your hypothesis sets. The difference, the gray area, acts like noise. And we're going to call this the deterministic noise. For computer science major students, you may think that this is like a pseudo-random generator. Okay, basically, pseudo-random generator is a deterministic function that generates random numbers. Here we have, even if we only have a deterministic target function, when that deterministic target function cannot be captured by our hypothesis sets, then the difference is like noise. And this particular noise can cause the learning algorithm to go astray. And that explains what we observed in the 50-degree polynomial case. In the 50-degree polynomial case, although there's no noise, the difference between 50-degree polynomial and all the hypotheses that we're considering is big enough that acts like noise to cause overfitting. To cause what to overfit? To cause the learner that picks from the 10th degree polynomial to overfit. Because even when it works the hardest within 10th degree polynomial, it cannot fit the noiseless target function or the noiseless data perfectly. And that difference acts as noise, causing the very big difference between the red curve and the blue curve. Now, the noise is also causing the restricted learner to deteriorate as well, because the performance can also be degraded given that learner H2 cannot fit the data perfectly either. But the effect for the more restricted learner is not that big, simply because there's less complexity. You are driving slower, so there's not that big a difference. Okay, so that's the first illustrative case we want to use to understand the interplay between noise, data amount, the complexity in learning, the model complexity in learning, and overfitting. Are there any questions? Okay, how is the E out calculated in page 7? Okay, let's go to page 7 and see. Okay, basically for those illustrative case study, we have some process that we use to generate the training data. Okay, much like possibly just a uniform distribution to generate the X, and then generates the Y correspondingly. So that's the P of XY that we used to generate the data. And we use the same P of XY to calculate the E out. Typically, what we can do, much like what we have learned in evaluating, in verifying machine learning, is to generate a lot more test data through the same process and then evaluate the learned hypothesis on those generated data and do an averaging. That's the E out we estimate, or actually that's E test, and we use that to represent E out. In this particular case, actually, given that we are using a very simple process to generate our data, we can also calculate E out analytically. Okay, so basically, using what you have learned in calculus and things like that. Okay, but those would give you similar numbers, basically. Is the expected error in P9 meaning noise? The expected error? No, the expected error is, okay, there are several things. Okay, one, you can view the converging value of those curves to mean some sort of noise. Okay, because noise is essentially what cannot be captured by our function. So that's one view. Okay, you can view that the expected error as noise. But for here, we don't really mean that in the noise sense. Okay, we mainly want to indicate E in and E out, which are values we can construct with respect to our data generation process. With data, with hypothesis, we can compute E in, we can compute E out, and the learning curve depicts that. Okay, depicts our computed E in and E out, and the expectation is taken over multiple rounds of generating data. Okay, so basically we're averaging over the data generation process, so we can get more meaningful numbers, not just on one data set, but on multiple data sets generated from the same process. Okay, great. Now let's move on to even more colorful pictures. Now we'll do a more detailed experiment, okay, that plays with several things. One, we will change our target function to be some polynomial, arbitrary polynomial of different degrees. And also we will be able to vary our noise level, okay, to arbitrary noise levels. We will have different degrees of target function to play with. We will have different noise levels that we will play with, along with different data sizes. Okay, so those are, think about it. Those are some of the factors that we can control in the data generation process in our previous case study to understand overfitting even deeper. And so basically we're playing with three numbers: sigma squared, the noise level; QF, the complexity of the target function; and the data size. What we want to study is the overfit level. Okay, and overfit level, we'll define it in a little bit later. The overfit level with respect to the number of examples and versus noise, the number of examples versus target complexity. What's the overfit measure that we're going to use? We're going to keep our previous study in taking H2 and H10 as just two particular cases, and we study the difference between E out. Because for H2 and H10, for G2 and G10, we already know that the E in would get smaller. We generally get smaller. We move to a much bigger hypothesis set, so if we do the right optimization, we will get smaller E in. Then the overfitting measure is just the difference between E out. If the difference is a lot, if G10 is of much higher E out than G2, then overfitting happen. Overfitting seriously happen. Okay, so we just take the E out difference as a measure of overfitting in our case study here. The results, let's check the first figure. We use a fixed target function with fixed complexity, 20-degree polynomial. We change the number of data points and the noise level. We get different values of the overfit measure. When the color is closer to red, the value is higher, more overfitting. And when the color is closer to blue, less overfitting. Actually, we're comparing the difference between the two E outs. So if things are below 0, actually there's no overfitting. Okay, no overfitting. Okay, so what do we observe? Where do we get more overfitting? We get more overfitting here. When we have very few data points and lots of noise in our data, that's when overfitting happens. Okay, when do we not get that much overfitting or no overfitting? When we have lots of data points, no noise. Okay, so that's the better area and of machine learning. And how about in between? When we get more noise in our data, more overfitting. When we get less data, more overfitting. Okay, so that picture clearly shows you when overfitting happens. And actually, it also shows you there are lots of cases where you can get overfitting. Okay, for example, you have a fixed polynomial 20 degrees and so on. Whenever there's noise, even if you have 100 examples, if the noise is too big, you can still get overfitting. Overfitting easily happens. Now, in another picture, we study the impact of target degree, where we say target degree would mean you have some noise within some complexity within the target function that cannot be digested by your hypothesis set, and that looks like noise as well. So if we take a fixed level of stochastic noise, but then vary the target degree, the more complicated you want to learn, the more possible you get overfitting. Okay, so if you want to learn a more complicated target function, you really need more data. If you don't have enough data, then the complexity of the target function that you may want to learn acts like noise and can cause overfitting. So in this part on the top, the behavior of target complexity is very similar to the behavior of noise. This justifies our argument that deterministic noise, basically the excess target complexity that we cannot digest, acts like noise, acts like the stochastic noise that we often see. Some of you may notice a different part, that is here. Why is there behavioral difference here? The behavioral difference is because we have 10 here as our target complexity. When our target complexity is much lower than 10, then overfitting is mainly caused not by noise, deterministic nor stochastic, but by excessive power. Right? Remember in the when we look at the part about overfitting, we say that excessive power can be a cause. And why do we have excessive power here? Because we are using H10 versus H2. So if you have a 7-degree polynomial, H10 has excessive power, much more than you need for a 7th-degree polynomial. So there's excessive power, and in this part, there's overfitting. When the degree of your target is lower, there's more excessive power and therefore more overfitting. So that's the behavior in that part. In summary, we see 3 causes of overfitting. But before we do that, let's just say this very colorful picture here is the logo of the Machine Learning Foundations course on Coursera. And there are 2 parts. One, overfitting in terms of stochastic noise, overfitting in terms of deterministic noise. There's linear model, there's nonlinear transform. Those are the very important tools that we have illustrated in this part of the class. And actually, if you look at that, the colorful picture is also the logo of the Learning from Data book. And this is a very important and hopefully beautiful picture that we'd want you to keep in mind. Now, stochastic noise versus deterministic noise, we have discussed about that. Then those pictures show us 4 reasons of overfitting. When we have little data, there's overfitting. That can be observed maybe here, here, and here. You just don't have enough data. If you have enough data, moving to the right-hand side, there won't be as much overfitting. That's data. And if there's more stochastic noise, you see more overfitting. That's basically the left-hand side figure. When there's more deterministic noise, you see more overfitting. That's what you see on the right-hand side figure on the top. And when there's excessive power, there's overfitting. That's what you see in the bottom here. There's more overfitting if there's a bigger difference between the power of your hypothesis set and the target function that you want to model. Overfitting easily happens. There are 4 causes that we show you with those beautiful rainbow-like figures, and we hope you to keep in mind. Okay, we have illustrated the deterministic noise by slightly changing the order of teaching. Let's see if we have any questions. Okay, the question here is, can we see underfitting in those pictures? And the short answer is no, or at least we need to change the design to do that, because we used G2 and G10, if you remember, and from G2 to G10, we have settled with decreasing E in. E in has decreased. Okay, and when E in has decreased, we are focused on studying overfitting, while it is not the case where we want to study underfitting. But of course, you can repeat the experiment, and possibly if you compare, for example, G2 with G1, okay, then you can use the experiment and perhaps redefine the overfitting measure, negate it as the underfitting measure. Then you will be able to use the same process to study underfitting as well. And another question is, why do we call the model complexity as deterministic noise? Just to highlight, we're not calling the model complexity as deterministic noise. No. Deterministic noise is the difference between the target function you want to model and the best hypothesis that you can get from your model. So what gets into the game is the target complexity in general. If your target is very complicated, while if your model is relatively simpler, the difference is deterministic noise. Okay, so what matters more is the target complexity, not the model complexity. The stochastic mean pseudo. Actually, for stochastic, it means stochastic. It means random, purely random, not pseudo. And when we're talking about pseudo here, usually we mean, okay, using a deterministic function to simulate a very complicated or random-like process. Okay, that's what people mean in pseudo number generator in typical computer science. Is it possible to share the program of overfitting figure? The program was not written by me, so I'm not sure if I can share it and so on. But it's actually not that hard to write the program by yourself if you have the data generation process and everything. You can check actually the resources part in the Learning from Data book, okay, to see if there are related figure generating codes and so on that you can play with yourself. What is the difference between less overfitting and underfitting? Okay, less overfitting means we're still overfitting. Okay, we're still getting an increased E in. Okay, while underfitting means we're still getting an increased E out. Okay, that means we're still overfitting. While underfitting means we are getting an increased E out, but while we increased E in as well. So underfitting is in a different zone. And when we are getting higher E in, higher E out, that's underfitting. When we are getting lower E in, slightly lower E out, slightly higher E out, we are getting less overfitting. How can we see stochastic noise on the graph? Okay, the stochastic noise, for example, we illustrated the experiment here. The difference between the black points and the blue curves are the noise. Blue curve are target function, but the black points are blue curve is the target function. The black points are not on the curve, and that means there's noise. There's stochastic noise that we generated, we added to the learning process here. What is the meaning of less than 0 overfitting index or overfitting measure here? Essentially, it means no overfitting. Okay, although we're not clearly highlighting that. Okay, but think about that. Okay, you are getting a negative value that actually mean you are getting a lower E out in G10 than G2. Okay, that means we're not overfitting yet. What's the relationship between excessive power and QF? QF is your target function. When your target function, the degree of your target function is lower than your model in this, your model complexity in this case, and then there's excessive power. Okay, so you want to a target that's 5-degree polynomial, but you use 10 degrees. Okay, then the difference, okay, the 5-degree difference is the excessive power. Does noise mean the difference between the target function and the real data points? For stochastic noise, yes. Okay, the target function, that was the one we plotted in blue. Okay, and the points, the real data points, are the black ones, and the difference is the stochastic noise we added to learning. And that's more specific to label noise, actually. Okay, but noise in machine learning has some different forms. For example, some people talk about feature noise and so on. But for here, we're just talking about additive label noise that we add to the process of regression learning. Okay, great. It seems that we have covered a pretty good part of overfitting today, and we're running out of time. In the next part, we will revisit the driving analogy and then tell you some practical approaches, some practical methods to combat overfitting. Okay, and we will visit some very simple methods and also some more widely used ones that you can actually see in a majority of machine learning model design. So look forward to seeing you in the next lecture. Good luck with your homework 2, and as mentioned, we will announce homework 3 soon. We will have start setting up the final projects for your team forming and so on. Okay, one very last question on Slido is whether we will release the answer of homework 1. We will not release the detailed solution. Okay, that's not going to be released. But generally, we will release the choice answer on Grayscope. Okay, that's what you will see when you get your graded performance. And also, if you have questions with any of the problems, you are highly encouraged to visit the TA hour or go to NTU Cool to ask those questions, and we can answer the questions, okay, to guide you to the actual answer. Okay, but we will not specifically prepare a release for the solution sheet. Okay, let me answer one last question here as it keeps coming. Too complex means too much order or function or too much power of x1. Okay, I'm assuming you mean the target function, and when you see the target function, you will see we deliberately use a very high order target function. Okay, that's visually looks very complex and so on, and you can think that you are describing this sort of complexity as, for example, how many parameters you use to specify this target function and so on. So this kind of complexity, meaning a higher order in terms of parameter choice, is what you can imagine to describe your what you want to learn. Okay, that's what we mean by target complexity, which is kind of similar to the model complexity or the hypothesis set complexity that we have learned. But now we're looking at a single function, the target function you have in mind, rather than a set of hypotheses. Okay, thank you very much for your active participation in the lecture today, and good luck with your midterms. Thank you. Bye-bye.